guys, in for the makeup lecture here today. Now that we're sitting down together, what I wanted to do is take a look at some of the series tests that we've been going over for the past couple weeks in class. Now to date we have maybe 8 or 9 tests that we've looked at so far, and I know that there's a lot and that's kind of overwhelming. So kind of the point of today is just to do a recap. The big question that I want to ask is, how do I know what test to use, right? And further, if I'm asking how do I know what test to use, once I know what test I'm using, how do they work? Because we've got a lot of these things going on right now, a lot of hypotheses to keep track of, a lot of rules to use, a lot of comparisons to make between different values that we can compute. Okay, so ideally it'd be nice if we could put everything all in one place. Okay, so you can have kind of a quick reference chart and how to apply each of our series tests. Now, kind of the outline of how this is going to work today, since I'm plowing through a lot of tests here, and there's a lot to look at, I'm going to kind of give you guys an outline as follows. Okay, we're going to group these tests by rough categories of what they fall into. Some of these are really fundamental basic tests that, you eyeball them, you get a result back super fast. Some of them are based on specific function types. So we're going to group these guys. I'll give you the name of my test. I'll try to give some sort of setup of red flags that we can look at that'll tell me, hey, this is probably a smart test to use. And I'll give you guys a reminder of some of my hypotheses and a brief example of a series that it would work with. Okay. Now, for brevity here, because I know you don't want to be sitting here watching this video for much longer than, an hour, there's a lot of tests. That means that would be a lot of examples here. For the moment, I'm just going to give, with these, examples of what kind of series it might apply to. I won't necessarily work out all of these examples. If you're interested in seeing more detailed results, you're welcome to stop by and ask me questions at some point later on. But I will give you an example of the series and what the actual result is, so you can check it out on your own, okay, and just confirm that you can get the same result that I'm saying happens with the test, right? And then at the end, we'll try and do a couple examples. All right, so let's go ahead and get started with my general format here. The first grouping of tests that I'm going to give you guys, these are my basic, series types, my really basic, fundamental series tests. These are the ones that you should be able to just look at the series and know what's going on. So, kind of my first one of these, this guy was my divergence test. This was one of the very first tests that I brought up to you guys. And kind of my red flag for this is basically the test in and of itself. If the sequence you are summing does not go to 0, you diverge. That's the test in a nutshell. If I can just look at my series and know that the thing that I'm adding doesn't go to 0, poof, just tell me you're using divergence test, and that's all the work that I need to see. You're using divergence test, I don't need to see anything else. Okay, so as a brief example of a series that this would apply to here, say I look at something like this guy. Okay, we'll look at the sum from n equals 1 to infinity of, let's say, n squared plus 1 over 10n. Right? Now, just looking at this guy, if I do my dominant terms trick on this, highest power over highest power is going to reduce to n over 10. This is not something that's going to go to 0, right? This will blow up. So, this guy diverges by this test, right? If you wanted to show work for this, the only thing I need to see is just the phrase divergence test along with this, and then you're in the clear. As far as other basic series that maybe I want to be looking at, another really early test that we covered. If my series is of the form I times r to the n, this guy is a geometric series. Okay? Geometric series, well, again, the red flag on this is basically looking for the format, right? The key component that I've got here that I really, really want to see, okay, my red flag that this is a straight up geometric series kind of problem, is I want to see some sort of number raised to the n. That's what a geometric series is. Maybe you have a coefficient out front, maybe you don't, but you've got some sort of a number raised to the n. Now, recall my hypotheses or my rules for this. Basically, if my absolute value of r is less than 1, we converge, and you are going to diverge otherwise. Okay? Fast examples of this. Say I want to look at something like, I don't know, let's say 3/5 to the n. Well, here my r is going to be this 3/5. That means that my absolute value of that is less than 1, so this guy converges. If I wanted to give you guys an example of a series that diverged, let's say I try something like 2 times 100 to the n. Okay, notice my r here is going to be bigger than 1, so this guy diverges. Now, fast kind of note here, if you are asked what this converges to, if it does converge, this is one of the very few cases in which we can pretty easily get back a value that it converges to. Okay, so if this guy converges, we've got a formula, right? And that formula was supposed to be a over 1 minus r. A is going to be the first term in your series, so take whatever your start number is, plug it in, that'll spit things out. I guess I should probably be gesturing to this guy because this is actually the one that converges. And your r is your thing that you're exponentiating here. Okay, so this is one of the few ones that we can actually tell ourselves what it converges to and get a formula for that. All right, one of your last ones of these basic series types are going to be p-series. These guys are going to be anything of the form 1 over n to the p, or things that can be rewritten in the form 1 over n to the p. Okay, my red flag for these guys, well, the format that I'm looking for is basically 1 over n to a number. Right? Before geometric series, we're a number to the n. Here we're seeing n to a number. Now, in this case, these guys are going to converge only when my p is bigger than 1. Okay? Recall the case p equals 1, this borderline case. This is a harmonic series that actually diverges. Right? So fast examples of this here, if I wanted to look at something like 1 over root n, regardless of whatever I want to sum over here, let's say I go from 1 to infinity just because it's pretty standard for us. Recall this is really a fractional power that we've got in the denominator. This is something I can think of as n to the 1/2. 1/2 is less than 1. That means that we don't converge. So this guy would diverge by my p-test. And if I wanted to give you guys an example of something that converged by my p-test, we just have to have this power be bigger than 1. Doesn't matter how much bigger than 1 it is, it just has to be bigger than 1. So if I wanted to do something like this and give you guys this long decimal, as long as I made it even a tiny bit bigger than 1, this guy still converges. Okay? Those were some of the really basic rudimentary tests that we got. Those are the fast ones, the super fast ones. You look at it, you've got the problem done in a couple seconds. some of the other tests that we'll move into are going to be a little bit harder for us to pick out. Okay, so I'm going to call kind of my next grouping here of tests that are based on specific function types. All right, so I can look at the kind of function that I have, and based on the kind of function that I have, it's probably going to steer me in the direction of a particular test. Okay, now to kind of come back to some of the earlier stuff that we've worked on, telescoping series, right? Remember those telescoping series? These were series of the form, okay, just kind of a fast example here. Say I looked at something like 1 over k minus 1 over k plus 1. I think this was an example that we did in class. Remember, we called these guys telescoping because we did sequences of partial sums to work these out. Okay, so if you see something specifically of this form, especially if you were asked to actually tell me what it converges to, cases like this, you probably wanted to do sequences of partial sums. Now, I know I've told you guys we really probably want to avoid sequences of partial sums as much as we possibly can, just because it's long and tedious and takes a while to write out. But, you know, if you're actually asked to evaluate this, this is one of the other very few cases that we could actually evaluate my series. And how you would do this is write out terms in your sum. Okay, cases like this, we called this telescoping because it would kind of come out and in and out and in and out and in, and we'd get all these cancellations between the terms that we were adding and subtracting and adding and subtracting. Okay, note where all your cancellations are. Note what gets stuck behind. Okay, and in a case like that, you can actually write this out, okay, and simplify this. Okay, so what's happening here is you probably want to write this out, cancel, and simplify. Now again, like I said, this is probably a case that we're going to want to try and avoid if we can, but if you are actually asked to evaluate and tell me what this comes out to, okay, we're probably stuck doing my sequences of partial sums because it's one of the few things that actually let us compute stuff. Okay, so, but again, that's a very specific function type, right? And we're usually looking for something basically that a function minus another function that looks really, really close to it. Okay, so be on the lookout for those. Other specific function types. These are pretty easy to pick out. If your series, your a sub n, has my a sub n alternating. Remember what alternating means. This is when you're adding up something that goes plus minus plus minus plus minus. Okay? If these guys are alternating, you probably want to try the alternating series test. Okay? So, in other words, if you got a1 minus a2 plus a3 minus a4, etc. Okay, now my red flag for these is, again, those plus minuses. This means you're probably going to see something that looks like minus 1 to the n or a negative number to the n. Or maybe you might see a cosine pi n somewhere in your a sub n. Right? These are going to introduce those plus minuses that we're looking for. Okay, now if I'm doing one of these tests, here are my hypotheses. So we're finally starting to get into some of the tests that actually had hypotheses to check. My hypotheses were, I basically wanted to find my positive part, okay, of the sequence I'm adding. We said that there was probably some sort of -1, +1 part that made this alternate between positive and negative. There's going to be a remaining part of this a sub n, I think in class we called it a b sub n. There's a remaining part of this function that actually kind of gives you the magnitude of the function. So it gives you the meat of what you actually are adding and subtracting each time. So find that positive part of the sequence, The hypotheses that we needed to verify were to check if it is decreasing and if it is going to 0. If so, that means that we converge. Recall, you've got some techniques in your tool belt for checking your limits, things like dominant terms, things like L'Hopital's rule. As far as decreasing, there are two ways that we could think about that. If you've got a fixed numerator and your denominator's blowing up, I'll take that as a justification that it's decreasing. Alternatively, if you've got that the derivative of whatever the heck your function is negative, I'll also take that it's decreasing. Okay? So, as an example here, and we've done this one in class, or one similar to it in class a couple times, standard example is something like the alternating harmonic series. Minus 1 to the n times 1 over n. This guy converges by my alternating series test. Okay? As far as other kind of patterns, things that maybe we might see that we can pick out that'll yell at me, hey, I should use this test. The negative 1 to the n yells alternating series if the thing that I'm summing, okay, if my a sub n looks like it's raised to an nth power, or something close to an nth power, maybe to the 2n or 3n, or to the negative n, you probably want to try root test. Now there's an exception here. If you've just got a number and it's raised to the n, that's geometric series. Geometric series are fast. Do the fast thing if you can, because it's less work for you. On the other hand, if you've got maybe like a function that's raised to the n, for example here, maybe I have n to the n, or 1 over n to the n, something like that, where it's not just a number to the n. Something like that, you're probably going to want to try root test. Now, the way that this guy works, okay, my hypotheses and my general rules for my test. Again, we're getting into the stuff that you need to check hypotheses for. What we're really going to examine here is some quantity that I think in class we called R. This is going to be the limit as n goes to infinity of my nth root of a sub n. So the thing, okay, that I was summing in the first place. The idea of why you probably want to try this on these things raised to the nth power is if they're raised to the nth power, this nth root is going to cancel that out. So we're going to examine whatever the heck this numerical value is, and there's a couple rules that you're going to follow. Okay? If your R is less than 1, you converge. On the other hand, if your R is bigger than 1, you are going to diverge. Finally, if your R is equal to 1, well, actually, you probably picked a poor test. This is going to be inconclusive, which means you need to try something else. This isn't going to tell you anything. Okay? So, the point of this test is, look for these things with nth powers, simplify this out, figure out what the number is, and you've got some comparisons to make to figure out what your test ultimately does. An example that I can try for here is, like I said before, maybe I look at something of the form 1 over n to the n. We've got a function that's raised to the nth power. If I wanted to look at this guy through this test, you can check pretty quickly this guy converges. Right? Once you hit this with an nth root, and then you try and take a limit of it, you're really taking a limit of this thing. And that's going to go to 0, right? So your R is going to shrink. It'll be less than 1, so you'll converge. Now, as far as another kind of function type that I maybe might look for here, and this is kind of a red flag, Do I see factorials? Okay, this is a big red flag for something like ratio test, right? Reason being, a lot of our tests involve taking limits or integrals, and we don't have a lot of well-defined rules for how to manipulate factorials unless we can get some cancellations going, and we get those cancellations by making ratios. Now, these are not the only kinds of things that will work well with ratio test. I just pointed this one out because, again, seeing that exclamation point, probably a pretty big red flag that you want to do ratio test. Other things that will work with ratio test, also, if I see products or quotients, so I'll go ahead and list both of these here. If I see products and quotients of mixed, not only factorials, but factorials, powers, and geometric looking stuff, this is probably a good sign for ratio test, because these were things that would give me these nice cancellations or, easy things that I could take limits of if I did ratio test. Okay? Now, at least as far as the hypotheses and my tests go, this is kind of similar to root test, except for we're examining a different R. You want to examine the R given by your limit as n goes to infinity of a sub n plus 1 over a sub n. I didn't write this out here, but this is probably pretty clearly examining the convergence of the series a sub n. How you get UR is you stick your original thing that you're summing in the bottom, you plug n plus 1 into that to get what you put up top, and you simplify this. And the rules for convergence are going to work exactly like root test, right? If your R is less than 1, you are going to converge. If your R is bigger than 1, you are going to diverge. And if your R is equal to 1, you probably made a poor life choice because this guy is going to be inconclusive. Okay, and that means you should go back and check another test. Okay, if I wanted to maybe try for a nice example of something that I could play with here, maybe I can try looking at something like this guy. We'll try n factorial over 3 to the n. Okay. If you want to play around with this, this is a good one to check on your own to make sure you got a handle on the test. You can show that this guy diverges with my ratio test. Okay? And as a side note, we've kind of have this notion of trying to figure out where these cancellations go and which functions end up going to infinity faster than others. And those are going to be kind of the ones that dominate the behavior of the series as n blows up. As a general rule, factorials are probably going to be stronger than these geometric-looking things. And the geometric-looking things are going to be stronger than your straight-up powers, so things like n squared, n cubed, etc. Okay, so in a case like this, you can kind of use that to help your intuition. It's obviously not going to count for showing me the work of the algebra, but for developing your intuition, since I just said factorials are stronger than geometric things, this means the top is probably going to dominate my behaviors and blows up. So yeah, of course, this guy's probably going to diverge. But again, work out your cancellations to show me the work for this, okay, if you're doing ratio test. Now, those were specific functions that I could pick out. Okay, maybe I see a minus 1 to the n. Maybe I see an nth power. Maybe I see a factorial. Okay, so things that I concretely have a hard, solid red flag to look for in applying these tests. These guys are going to be a little bit more subtle. So my last category that I've got here for you guys These are going to be my more general function types. Another thing that I'm going to point out, and the reason that I kind of suggested these in this order, if you've noticed, I've tried working from easier tests to the harder ones. As a general rule, you want to try to see if you can do your easier stuff first to save yourself the headache of trying a harder test and not having it work, right? So think through what your easiest possible thing is going to be to work on a function, okay, and then maybe think about the harder stuff from there. Probably a next test that we could try looking at here is given by the following red flag. Now, when I say more general function types, I can ask, does your a sub n that you are summing up, does this look approximately like a geometric or p-series? Or maybe a fraction composed of such. Okay, so things like rational functions. In a case like this, you probably want to try your comparison test or your limit comparison test. Now, I'm going to give you guys a hint. By and large, most people that I've ever taught these to find limit comparison test a lot easier to work with. In pretty much any case that you can use comparison test, you can use limit comparison test, and vice versa. So, again, if you've got a choice, probably better for you if you pick the easier one. Now, if you're one of those far and few between people that, for whatever reason, comparison test is easier for you, do that instead. Okay, but some of the highlights that I see for this, remember, comparison test was going to be the one where we set up an inequality, right? So I guess I'll go ahead and write these out here, since I did say that I would remind you guys of the hypotheses for this. For my comparison test, we said that my hypotheses were I need basically positive terms everywhere. I need to set up an inequality to compare my a sub n to, right? I'm comparing my a sub n to a b sub n. Okay, and the general idea is if you are bigger than a divergent series, you diverge. If you are smaller, then you converge. And the reason that this is kind of tricky for most people is getting the direction straight on the inequalities is kind of hard, right? We get the idea of what to compare this to usually by looking at dominant terms, and that's not really the hard part. And the hard part is getting this to match up so it goes in the right direction. Now, for limit comparison test, what you do, and my hypotheses here, are you still want positive terms, but again, instead of setting up this inequality that we're trying to compare a sub n to, so instead of trying to find a b sub n and match this up in the right direction, what we're probably doing is, look for a b sub n to approximate your series. Okay, look for a b sub n to approximate your a sub n. You want to set up, okay, guess I'll call this c. This is your limit as n goes to infinity of a sub n over b sub n. And if c is a finite positive number, so if it's positive and not 0, not infinity, my a sub n and my b sub n do the same thing. Notice we don't have to think about which direction this goes. You just crank out a limit and look for a number. And if that number is positive, which assuming you picked a good b sub n, it will be, these are going to do the same thing. So this is usually less thinking than this guy. I would probably recommend doing limit comparison test if you have to do one of these. Okay, now as an example here, since I did say I'd give an example for pretty much each of these, you can show that a series like 4 to the n over 5 to the n plus 1, this guy, converges. Idea being, if I look at dominant terms, it's very approximately going to look like this, which is a geometric series, and it's a geometric series with r equals 4/5, right? Since that guy converges, this is probably going to converge too. And the rest of it is just going to be in the details and showing either your limit or your inequality are straight. Now, last of the tests, this is actually one of the first ones that we did in class. I mentioned these were kind of more generic function types. I'll ask, does it look like her function has an easy integral? Okay? If you're seeing things like, natural log of n over n, where there's maybe a clear u substitution, or it just looks like it's something easy to integrate otherwise, well, easy integral probably means you can try integral test. Okay? Now, one of the reasons why I suggest this one last, again, I've mentioned, you kind of want to try the easy test first, if possible. This guy actually requires a good amount of work, in that there's hypotheses to check, and you have to compute an integral here. Remember, your hypotheses are that your function has to be continuous, it has to be decreasing, and it has to be positive. And in that case, once you get those hypotheses, your series does the same thing as your integral does. Okay, basically whatever bounds you had on that series, you treat them as bounds on your integral, and you integrate the thing that you're adding up. Okay, so lots of stuff to check, and additional computation thing to work out. So usually this one's kind of a bit of work. Now, minor note, when I say the series does the same thing as the integral, I mean convergence or divergence. I don't mean actually summing up to the same thing, right? So, for example, since I did say I would list a couple examples here, you could show that a series like this, look at my sum from 2 to infinity, 1 over n natural log of n, this guy diverges. Okay, and some hints on setting that up. What you're doing is setting up the improper integral from 2 to infinity of this function. And if you'll notice, this looks really right for a u substitution because we've got a natural log of n and a 1 over n here. Okay, so this is going to be something that you should be able to set up a pretty nice u substitution for. Set this up as an improper integral. Okay, after showing that this is continuous, it's decreasing, it's positive. Okay, and you'll get that the integral diverges. So the series has to diverge. Okay, so that's burned us through the majority of our tests. What I wanted to give are a couple general notes for usage of all of these. Okay? What I would probably say, again, I really want to emphasize this, sometimes more than one test works. When in doubt, please try the easier ones first. Okay, so please try the easiest first. I'll give an example. Say I'm looking at something like my series here, n equals 1 to infinity, 1 over 2 to the n. There's a number of ways you could do this. If you really wanted to, you could set up integral test for this guy. If you really wanted to, we could do sequences of partial sums and actually compute that this is something that converges. If we really wanted to, we could do root test on this. Or you could recognize this as a geometric series with r less than 1. Okay? Your call. We've got options for this guy. One of them is clearly much better than the others. Okay? Which, again, one of the reasons that I posted these in the order that I did, usually works best to try and start at the beginning of the list of the stuff that I've mentioned so far, and then try and, work through to the end. Okay? Another comment that I want to make is most of my tests basically give convergence or divergence info and not what the actual sum is. Geometric series, you have a formula. If you're doing sequences of partial sums, you have an actual formula. You really don't have much else. Most of these numbers that you're finding, if you're doing integral tests, you get a value back. Maybe that might be an approximation for a rough value that you could come out to, but you're probably overshooting your series or undershooting your series a little bit. If you are looking at something like ratio test or root test and finding R was just your comparison value. Doesn't tell you what it adds to. If you're doing something like limit comparison test and finding C, this is not what it adds to. C was just a comparison value, okay, that we can plug into our test. Okay, so don't think that a lot of these actually give you the sum. Only sequences of partial sums and geometric series, for the most part, are going to be the ways that you can get actual values back. Okay, so if you're asked to compute something, probably a red flag. It's one of those tests too. Okay, and another thing, kind of the final warning that I'll give you guys for general usage of all of these tests. I've had a lot of questions on how to show your work. Okay, what do I need to show? What will get points taken off? What absolutely positively needs to be there? If you are using a test, this is probably what I expect. If there are hypotheses for it, you probably need to state them or explicitly check them. Now, there's some tests that there really weren't much to, and I won't really need to see much for that. For example, divergence test. You're just checking that the limit of the sequence that you're summing up doesn't go to 0. Something like that, just state the limit's not 0. Divergence test, done. I'm not really asking for a lot of supporting work in checking some of the hypotheses. Like, for example, for integral test, you need a continuous function. If you note that a continuous function is continuous by writing continuous and putting a check mark, I'll probably count that. It'll be fine. Okay? But if you're doing a test that's got any hypotheses at all whatsoever, tell me what those hypotheses are. If you're using a test that has you do computations, okay, do you need to find an R? Do you need to find a C? Do you need to find some sort of integral? Okay, do you need to find something else? A lot of these are based off of giving me some sort of numerical value and comparing that numerical value to a standard to give me divergence or convergence results. If your test involves that, you need to show me the supporting work. Okay? This last one, it always makes me sad when I take points off for this. If you're using a test, let me know what test you're using. So if you're using root test, say root test. If you're using ratio test, say ratio test. Okay? So please, 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 please state the name of the test you're using. Okay? And a very, very similar comment that it also kind of makes me sad whenever I take points off for this. You would think this is obvious. State that it converges or diverges, right? If you're trying to do a test. Now, as an example, and this is probably a really common one, if you're doing a geometric series problem and you state, oh, R is less than 1. Sure, I know what you probably mean there, but unless you explicitly come out and say it, you haven't actually answered my question, right? So particularly on these problems where your result is hinging on one of these computations, if you tell me what R is, if you tell me what C is, and you leave the problem there, you're not done, okay? So, how I'm looking for you guys to show your work if you're doing pretty much any of these tests, your general rules to follow are give me a hypothesis, state them, check them, at least in some minimal sort of way, acknowledge that they exist and that you know what they are for each of the tests. Give me any relevant computations that you need for limits or things like that. State the test and give me your result. Okay, so I'll try to see if I can maybe do a brief example here, particularly of one of these that maybe I can tackle a couple different ways. Say something like n squared over n squared plus 1. Actually, let's clean this up so it's a little bit more exciting. The n squared over the n squared would have given me a limit of 1 here, so that would have diverged pretty fast. We'll try this one. Okay? If I'm looking at this guy and I plow through my list, you notice this isn't a basic series. It's not P. It's not geometric. My limit goes to 0 in this case because I changed up my example, and that means divergence test doesn't work. So, again, try and run through your list of possible tests and, what some of the red flags are and whether it meets it. One of the red flags that maybe I could point out here is that this looks a little bit like a P-series, but not quite, because of the stupid 1. So maybe one thing you could do here is one of the comparison tests, or the limit comparison test. Another option that maybe you might have is this looks like something that we could integrate pretty easily, right? We've got a square on the bottom and an n up top, so this looks pretty ripe for a U substitution. This is one of those cases that more than one test works. Right, so I'll try and give you guys an example of how to do this both ways. Let's see if I can try my limit comparison test first. All right, if I do limit comparison test, we need to make note of the fact that we've got positive terms here. We also need to make note of what we are comparing this to. My dominant terms are going to suggest that probably 1 over n, after I cancel, is a good comparison. So let's see if I can try to compare to b sub n equals 1 over n. And how I do this is I set up my limit out at infinity of my a sub n, my original thing that I'm summing, over my b sub n. Okay, my limit here is going to be n over n squared plus 1 divided by my b sub n, which is 1 over n. If you are dividing by a fraction, it's the same thing as multiplying by a reciprocal. So I'm really multiplying by n here. This will be n times n over n squared plus 1. And you'll notice my dominant terms here are going to give me a limit of 1. So, I've stated my hypotheses, I've got my positive terms, I've done my computational work, which gives me my C. Here I can note that my C is a finite positive number. So, this does the same thing as my sum for my b sub n. Now, notice my b sub n was 1 over n. This is a divergent p-series. So, my original series diverges by my limit comparison test. Okay? Now, that's one way to do it. Let me see if I can squeeze my integral test in here on the other side. If I want to try my integral test, we had a couple hypotheses to check. Namely, is this guy continuous? Yeah, there's no divide by zeros or anything weird on the interval from 1 to infinity. is this guy decreasing? Now, I probably want to check my derivative here because both my numerator and my denominator are increasing. Here, my f prime is going to be low d high, which is 1, minus high d low, which is 2n, all over low squared. This is going to be the same thing once I simplify this as, well, my n squared minus 2n squared is going to give me 1 minus n squared. Now, for this particular function, notice the bottom is always positive, and the top, well, on the interval from 1 to infinity, n squared is always going to be 1 or bigger. Now, this maybe doesn't meet the hypotheses at 1, but I mean, it's not really going to need to meet the hypothesis at 1 because, 1 isn't decreasing from anything. 1's your first term. So effectively, this is going to be negative everywhere. And if this is negative everywhere, this is going to be decreasing, right? So this is negative where it counts. We're going to have a decreasing function. Now, the other thing I need to check is this guy positive? Well, n is positive, n squared is positive, 1 is positive. Again, I probably don't need a lot of work from you guys. Just acknowledge that the hypotheses are there. Okay, so we got a continuous decreasing positive function. Set up the integral and see whatever the heck it does. My integral is from 1 to infinity, for the same function that I'm looking at right here. And if I set this guy up, notice that we've got, this is pretty well set up for u substitution, right? Notice I can do u is n squared plus 1, du is 2n dn, so this is going to tell me 1/2 du is n dn. If I try to evaluate my integral here, I'm going to get a new set of bounds. I'll plug these in to get my new bounds. This is now going from 2 to b squared plus 1. And this is going to look like 1/2 over u du. Well, this integrates to 1/2 times natural log of u, evaluated between 2 and b squared plus 1. And basically, if I try and take my limit here, we plug in the top value first. Natural log of b squared plus 1 minus 1/2 natural log of 2. Notice, I kind of have to carry this over to another page. This 1/2 natural log b squared plus 1, this is going to go to infinity, right? So this integral basically goes to infinity, and what that tells me is that my integral diverges. By my integral test, this is going to tell me that my series diverges too. Okay? Now, what I wanted to go ahead and do, since we've highlighted one of these functions that maybe we can do a couple different ways, I want to give you guys a problem that you can look at and see if y'all can work it out for me. And also give kind of a freebie problem to work too. This is a problem that can be evaluated using at least 2 of the methods that we've talked about here. Okay? N times e to the negative n squared. So I'm going to have you guys do this one for me. This is going to be one of the tests, which is going to involve some computation for us. You've got at least 2 options that I know of will work for this, so choose carefully. And I'll throw on a really fast one. Tell me also what this does. Okay, let's take a look at, let's say n to the 4th plus 5n plus 3 over 6n to the 4th minus 5. I promise, if you catch the trick, this is really, 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 really fast. And this should show, you'll probably need basically no work for this. Okay? So my quiz. Turn me in both these integrals. If you guys have questions, feel free to let me know, or try and see if you can contact me by email.